This image is generated by one of the smallest mathematical rules ever studied, and inside it is infinity. Not poetic infinity, not a lot of detail, real infinity. You can zoom into this shape forever, and no matter how deep you go, new structures keep appearing. And somehow, all of this comes from a single equation. So how can an infinite world exist inside something so small? We grow up with a very reasonable idea. Simple rules create simple results. If something looks complicated, it must have complicated causes. After all, nature looks messy. Clouds, coastlines, turbulence. Nothing feels simple. This idea wasn't just philosophical. In the 1960s, a meteorologist named Edward Lorenz discovered something unsettling while simulating weather. He restarted a simulation using numbers rounded slightly differently, just a tiny change, and the result completely diverged. The equations were deterministic. There was no randomness, yet outcomes became impossible to predict. Lorenz realized something profound. Simple rules don't always lead to simple behavior. Sometimes they lead to chaos. Around the same time, another mathematician was asking a different question. His name was Benoit Mandelbrot. He wasn't studying motion or time, he was studying shape. Clouds, mountains, coastlines. He asked something that sounds almost ridiculous. How long is the coast of Britain? The answer depended on how closely you looked. The more you zoomed in, the longer it became. Nature, Mandelbrot realized, doesn't smooth out when you examine it. It becomes more detailed. That idea needed a new kind of geometry. Mandelbrot suspected this roughness wasn't exclusive to nature. He believed mathematics itself could produce it. The Mandelbrot set is where that belief becomes impossible to ignore. To see how, we need one new kind of number, a complex number. A complex number looks like this: a plus b, I. Here, a and b are normal real numbers, and I is defined as the square root of -1. That might sound strange, but the idea is simple. No real number, when squared, becomes negative. So mathematicians extended the number system with I so that I squared equals -1. Once numbers have two parts, real and imaginary, they can't live on a line anymore. They live on a plane. Horizontal axis, real part. Vertical axis, imaginary part. Now, every complex number is a point on this plane. Simple operations suddenly become more interesting. Adding complex numbers moves the point around, like sliding it across the plane. Squaring a complex number does two things at once. It stretches it farther from the origin and rotates it around the origin. So a single simple operation, squaring, can make a point spiral, orbit, or fly away. Motion emerges from nothing but math. Now here's the tiny rule that produces everything. We take a number, call it z. We square it. Then we add a fixed number, c. Written simply, z equals z squared plus c. That's it. No randomness, no if statements, just repetition. Here's how we use it. Pick a value for c. That value stays fixed. Start with z equals 0. So the first step is z1 equals c. Then repeat. Square z, add c, repeat. We ask one simple question. Does this sequence stay bounded, orbiting somewhere? Or does it explode toward infinity? Every point you see in the Mandelbrot picture is one value of c. If repeating the rule stays stable, that point belongs to the set. If it blows up, it doesn't. Color the escaping points. Leave the stable ones dark. And suddenly, a shape appears. After showing the full set, this is the moment you feel it. That incredibly detailed boundary, the endless swirls, is not created by a complicated program. It's created by repeating this tiny rule. Because the rule is so simple, the surprising thing is not that the fractal exists, it's that it's so complex. And it gets weirder. The exponent in z squared plus c doesn't have to be 2. Try z cubed, or z to the 4th power, or z to the 5th power. Each one creates a different universe, different symmetries, different structure, different kinds of infinity. The Mandelbrot, is just the most famous member of a whole family of fractals.
But there's something even more fascinating. The Mandelbrot set is not unique. It belongs to a vast family of fractals. Many shapes in this family are like cousins, all born from similar, simple rules. Take Julia sets, for example. For each point C in the Mandelbrot set, there's a corresponding Julia set, another infinite world with its own swirling beauty waiting to be explored. Some look like flowers, some like lightning, some like delicate webs. In fact, you can think of the Mandelbrot set as a map of all these worlds. It's like a catalog of infinities, each generated by a tiny equation, each revealing its own version of complexity. And this isn't limited to just the formulas we've mentioned. Mathematicians keep discovering new variations, each producing its own endless patterns. The Mandelbrot set is just the most famous example, one gem in a treasure chest of infinite possibilities. And there are even ways to measure how close a point is to the edge, ways that can turn this flat image into mountains, or tricks to spot repeating patterns early, or track tiny errors as we compute. Even the hardware inside our computers has secrets for rendering these worlds. But that's another rabbit hole. Everything you've seen so far depends on how we choose to look. When we draw the Mandelbrot set, we usually color points by how fast they escape. That's why you see sharp bands of color. But those bands aren't really part of the Mandelbrot set. They're artifacts, created by counting the iterations in whole steps. When mathematicians let that count become continuous, when they measure how a point escapes, not just when, suddenly hidden textures appear. Structure between structures, detail between the details. Even infinity had more inside it than we first thought. Now a practical problem appears. Mathematically, these worlds are infinite. Computers are not. As we zoom deeper, the numbers demand more and more precision. Eventually, the computer can't even tell two nearby points apart. Infinity exists, but our tools start to fail. So how do we go deeper? Mathematicians don't usually try to outcompute infinity. They cheat it, cleverly. They notice that if 2 points start extremely close together, their early behavior is almost identical. So instead of recomputing every pixel from scratch, you follow one orbit very carefully and describe nearby points as tiny deviations from it. It's like tracking the main road and only keeping track of the small detours around it. That part is called perturbation. But to make this useful, you need a way to describe how nearby pixels differ from that main orbit. So instead of recalculating everything, you write those differences as a small expansion, a series of corrections that stay accurate while the points remain close. That's series approximation. Together, these ideas let computers zoom deeper without losing precision or exploding in cost. Perturbation tells you what to track. Series approximation tells you how to reuse it. It's not about shortcuts. It's about understanding how tiny differences grow. The same thinking appears in weather prediction, physics simulations, and many numerical methods. When exact calculation is impossible, smart approximation gets you surprisingly far. So what does all this mean? The Mandelbrot set isn't complicated because it's random. It's complicated because it's precise. Every swirl is inevitable. Every pattern determined. Infinity didn't need infinite rules. It only needed a simple rule, repeated forever. When we see complexity in nature, we often assume chaos. But sometimes complexity is not disorder at all. Sometimes it's a tiny equation, quietly unfolding into infinity.